Okay. Core 65 LP SVT is the library that you should use to get prefabricated gates and inverters and stuff like that. So I take this inverter, oops, I place one here, one here, one here, one here. Whenever you want to simulate anything, circuit-wise, you provide your inputs via an inverter to create more accurate conditions for your circuit. No, not stable. It's because when you simulate, you usually use a pulse voltage or something, and that's not a real. It's not similar to a real life signal. It's perfect signal. So the inverter will produce a signal that's similar to a real life signal you'd find in circuits.
In this case, we need two inverters to
usually you put an inverter on every
count for the inverter. So if I wanted to one, just
actually I should have put two inverters in series to but it's okay.
Can we use a buffer instead?
I guess so. Yeah, we could use a buffer. By the way, this out here does not conflict with the out here because they're in different domains, in different hierarchy level. Okay. Now I save my circuit. I have one warning somewhere. What is that? You see the warning? I guess these two are too close to each other. Never had that error before. Just move it. Okay, I'm good to go. Okay, now there's a different tool to perform our simulation. From the schematic window, we go to Tools and choose Analog Environment. That is where we go to simulate the circuit. Okay. Now, this is our circuit simulator. Usually, you should go through all of these menus one to one to specify our simulation parameters. Now, session is if I want to save my simulation parameters and configuration so that I don't have to put it again and again, so I save my session here. I'll do that later. Okay, first thing is you set up your simulator. Here I choose Spectre. Spectre is a simulator just like Spice. And over here, now the simulation will generate a lot of temporary files and stuff, and if you choose it in your home directory, it will potentially fill up your account with junk files. So to prevent that, you put the simulation directory as /tmp. Okay? Now, model libraries, you don't need to do anything here. Here you specify the temperature. Let's just keep it at 727. Stimuli, this is very important. Now notice here we have inputs and global sources. In global sources, we should have had VDD and ground here. I don't know why we don't. Let me check it again. This is strange.
Do we need to combine it or just to simulate the actual schematic?
What do you mean?
I mean, I used to, when you have a schematic, you need to convert it and compile it into some source of code and then simulate that code.
Oh, like convert it to Spice and simulate it?
Yeah, something like that, yeah.
No, it will do it automatically, built in. Okay, now, I don't know what the problem here is. I must have missed something, so instead of simulating this circuit, I'll just simulate this one right ahead. Okay. Okay. So change this to temp. Okay. Okay. This is what you're supposed to have in global sources. So I put enabled, I choose DC, and I give it a value of for 65 nanometer, we choose 1.2 volts as VDD. Okay. So we choose 1.2. Click on change, and we go to inputs. And here I wanna put pulse waves. Choose pulse. One point two. 0. The rise time you should keep it as 30 picoseconds. Pulse width is usually half the period. Let's make it as 0.5 nano and period as 1 nano. Okay. Now for B, do the same thing.
You selected the value of 1 as 1.2 volts?
Yes.
So I have a question.
Yeah.
Can't we, using this run without, can we remove the buffers and just, the inverter, and just make this as real as possible?
Yeah, you can. This is why we have rise time and fall time to make it.
We can
Yeah.
specify that and just remove
Sure,
it.
but the problem with this is the supply voltage has unlimited current. It can supply unlimited current. But from an inverter, the driving capability of an inverter is limited, which is more similar to a real situation. And here it's always whenever you want to simulate stuff with pulse waves, it's always a good idea to always double the period from one pulse wave to the other, so that you have all possible combinations.
Sometimes the number of inputs will not allow you to
Right. If it's a lot of inputs, then you probably should do DC. Then DC is It's probably easier. Okay. So we finished the stimuli part. Now we choose our analysis. What do we normally choose here? Do you guys remember? What type of simulation? Yeah. So we have actually a bunch of them. If you're curious, you can go ahead and try. We need to simulate for 4 nanoseconds. Choose enable. Okay. And then for variables, you can actually you can have variables in your circuit, such as the width of a transistor or a value of a capacitor or a resistor, and you can specify it from here if you want. But we don't have that right now. Now these are the outputs, meaning the plots, the graphs that we want to see from the simulation. You choose to be plotted, select on schematic. It takes us to the schematic. I want to see A and B and C and out. Okay. Now it adds them here. Now before I run my simulation, there's one thing I need to do, and this should be new to you guys. I go to Tools, Setup, Corners. Okay, now the concept of corners is very popular in the industry. When you manufacture a chip, sometimes not all the transistors are equally strong. Some transistors come out faster than others, some come out slower. It's because of imperfections you have in the fabrication process. So to simulate this imperfection in the manufacturing process, we have something called corners. They call it corners because one corner is fast, meaning the PMOS are fast, the NMOS are fast. Another corner is fast, slow, FS, which is fast PMOS, slow NMOS. So we have FF, FS, SS. We have multiple corners that simulate imperfections in fabrication. But for now, we're just going to use TT. TT is typical, meaning the NMOS are typical and PMOS are typical.
So which type of transistor present the first layer? Is it the PMOS or
I actually forgot, but I have to check. I forgot. The first thing we do is TT. You can see we have FF, FS. I don't know what FFA stands for, but
isn't the second one typical?
I don't know. It's confusing. But usually you only need to do typical unless you're submitting a paper and you need to show the people that your circuit works in all kinds of circumstances. Here you choose no, and here you choose DK, and then save model file. Close up. Okay, now we're ready to run our simulation. We choose netlist and run.
This is the part where he asked about.
Yeah, here it will create the netlist automatically. You can actually view the netlist if you want. And this is my simulation output. I can separate the graphs if I need to, like that. This is not scaling. Anyway, you can see your outputs here and measure them on the graph. Is that good? Is it easy enough? No?